welcome. We have seen till time that we can use the Rankine cycle for electricity generation, and also we can use the Rankine cycle for the effects where we are actually having waste heat, or we are having the heat to be supplied where steam is the source of the high temperature, constant temperature source. So, the examples were bypass turbine or the back pressure turbine, and also electricity generation we had seen. Then we had seen that there are some properties of ideal fluid, and looking at those ideal fluids we had come to a conclusion that there is need of binary or tertiary fluid cycles. In that case we had seen that we can club two Rankine cycles together, and if we club two Rankine cycles together, then we will have higher efficiency of the coupled cycle. But we have also seen in last class that the Rankine cycle coupling is a problem, since it has issues like high cost and the leakage. So the most possible way to couple is coupling of Rankine cycle with Brayton cycle. So we had seen what do we mean by Brayton cycle. Further we are going to see in this class that how we can make use of Brayton cycle and Rankine cycle in coupling, and also what are the possible low temperature cycle. So coupling of gas turbine cycle and steam turbine cycle. So we had seen in last class that we will have gas turbine cycle at the topping cycle. So this is our topping cycle and this is our bottoming cycle, and in this topping and bottoming cycle we have compressor from A to B, where it is increasing the pressure of the gas, which is the gas used in the gas turbine cycle. Then we will have heat addition into the heat exchanger. This is heat exchanger. So in the heat exchanger we will add heat. Once heat is added into the heat exchanger, then we will have expansion in the turbine, and in the after expansion in the turbine, the gas turbine cycle will lose the heat, and this heat lost will be taken by the water which is pumped first to high pressure, then it will take the heat into the boiler, which is necessarily the heat exchanger for gas turbine cycle, and then we will have expansion in the steam turbine, and then we have condenser which will remove the heat. So having said this, this is the schematic we had seen, and then we have this as the TS diagram for topping and bottoming cycle, where we have this as gas turbine cycle and this as Rankine cycle, where we are supplying the heat from the gas turbine cycle to the Rankine cycle. Unless otherwise said, we will consider the total heat to be exchanged in this process, or we will have to be said otherwise that only latent heat is exchanged or latent heat is given from the Brayton cycle. So if efficiency 1 is the efficiency of Brayton cycle, efficiency 2 is efficiency of Rankine cycle, we had proved that total efficiency or efficiency of the combined cycle is eta 1 plus eta 2 minus eta 1 into eta 2, and this eta is actually greater than eta 1 and eta is also greater than eta 2. We had seen this point, we have proved this. Having said this, let us consider that we have now Rankine and Rankine cycle or Rankine and Brayton cycle with some loss. That means we have topping cycle, this is 1 is a topping cycle and this is 2 is a bottoming cycle. So we will say this as T and then this as B, topping and bottoming cycle. So Q1 is the heat taken by the topping cycle. It loses Q2 amount of heat and does W1 amount of work. But in this process it loses QL amount of heat before passing the heat Q3 to the bottoming cycle. So in the last expression where we had proved that eta 1 we have proved here that eta 1 plus eta 2 minus eta 1 eta 2 is equal to eta. In this case we had assumed that QL is equal to 0, so we don't have any loss. But now if we have loss, then we will have to prove what is the efficiency. So efficiency, we know that total efficiency of the combined cycle is equal to W1 plus W2 divided by Q1. Q1 is the heat taken total from the atmosphere surrounding, where eta 1 is the efficiency of topping cycle and eta 2 is the efficiency of bottoming cycle. Eta 1 is equal to W1 upon Q1 and eta 2 is equal to W2 upon Q3, where Q3 is the heat taken by the bottoming cycle. Then we have Q3 is equal to, from the heat conservation, Q3 is equal to Q2 minus QL, Q2 minus QL, but Q2 can be found out as Q1 into 1 minus eta 1. Okay, so this is Q2. Since we know that W1 is equal to Q1 minus Q2, or eta 1 is equal to 1 minus Q2 upon Q1. So this formula can give us that Q2 is equal to Q1 into 1 minus eta 1. This we can obtain from here. So we know now what is Q2. So Q2 is equal to 1 minus eta 1 into Q1 minus QL. So this is formula for Q3. So we can say that we have now eta is equal to eta 1, W1 upon Q1 is eta 1 plus eta 2 into Q3 upon Q1, W2 upon Q1, but W2 upon Q1 can be expressed as eta 2 into Q3 upon Q1. Since we know that we can express this expression, eta is equal to W1 plus W2 upon Q1 is equal to W1 upon Q1 plus W2 upon Q1, but W1 plus upon Q1 is eta 1 and W2 upon Q1 can be expressed as W2 upon Q3 into Q3 upon Q1. So eta is equal to eta 1 plus W2 upon Q3 is eta 2. So this is eta 2 into Q3 upon Q1, and this is what we have written here. So this is eta 1 plus eta 2 into Q3 upon Q1, but Q3 upon Q1 can be expressed from this expression as Q3 upon Q1 is equal to 1 minus eta 1 minus QL upon Q1. So this is what expressed over here in the bracket. So we have got total expression for eta is equal to eta 1 plus eta 2 into bracket 1 minus eta 1 minus QL upon Q1. So having said this, we will represent, suppose XL as a factor, loss factor is equal to QL upon Q1. So this term is said as loss factor. Having known this, we can write down the expression as eta is equal to eta 1 plus eta 2 minus eta 1 eta 2 minus eta 2 XL. So this comes an extra term with loss. This term is giving us the efficiency without loss, and this efficiency gets subtracted due to loss. Further, we can also find out using different method where we will say that eta B is some loss coefficient which is equal to Q3 upon Q2. Q3 is the heat taken by the bottoming cycle and Q2 is the heat lost by the topping cycle. So, Q3 upon Q2, and then that is equal to 1 minus QL upon Q2. So, this eta is as if we are running a cycle and then that has an efficiency which is operating between Q2 and Q3, or we can also say this as a equivalent loss coefficient which is equal to 1 minus QL upon Q2, since Q3 is equal to Q2 minus QL. So, 1 minus QL upon Q2 is equal to eta B. So, having known this, we can write down eta is equal to W1 plus W2 upon Q1, and then it is equal to eta 1 plus eta 2 into Q3 upon Q1. So, this is equal to eta 1 plus eta 2 into eta B into Q2 upon Q1. Again the same thing here, Q3 upon Q1 is written as Q3 upon Q2 into Q2 upon Q1, where Q3 upon Q2 is eta B into Q2 upon Q1. So, we get the expression eta 1 plus eta 2 into eta B into Q2 upon Q1. Having known this, we can represent eta 1 plus eta 2 into eta B into 1 minus eta 1 is equal to eta 1 plus eta 2 eta B minus eta 1 into eta 2 into eta B. So, these two expressions are the representations in terms of the loss coefficient or loss factor. Overall, we can also write this efficiency, which is a gross efficiency, is equal to eta 1 plus eta naught 2 minus eta into eta naught 2. So, this term is called as eta naught 2, and then that is where we can get the efficiency as eta 1 plus eta naught 2 minus eta 1 into eta naught 2. So, this gives us an idea that how much loss in efficiency we will have if the heat lost by one cycle is not equal to the heat gained by the other cycle. Now, we had seen that we are coupling two cycles where one is topping cycle and other is bottoming cycle. But an obvious question which would come to our mind that why don't we have two cycles in parallel, and this would be an example for that, where we have two cycles, cycle 1 and cycle 2, and these two cycles are in parallel, where they are getting heat from a common source which is having supplying heat Q1. Among that, Q2 amount of heat is supplied to cycle 1, Q4 amount of heat is supplied to cycle 2. Cycle 1 does W1 amount of work, cycle 2 does W2 amount of work, where cycle 1 rejects Q3 amount of heat and cycle 2 rejects Q5 amount of heat. Let us see what will happen if we have eta 1 and eta 2 are efficiencies, then what would happen as the total efficiency of the cycle. Let us say that eta 1 is efficiency of cycle 1, eta 2 as efficiency of cycle 2. So, we know that W1 work done by the first cycle is equal to efficiency of the first cycle into heat supplied to the first cycle. Similarly, heat work done by the second cycle is equal to efficiency of second cycle into heat supplied to the second cycle. Then we know that total efficiency of the cycle is equal to W1 plus W2 upon Q1, but Q1 is the total amount of heat supplied, which is equal to Q2 plus Q4. which is Q2 plus Q4, but W1 can be written from here as eta 1 into Q1 and W2 can be written as eta 2 into Q4. Having known this, we can write down this expression using a constant where we will say x1 is equal to Q2 upon Q2 plus Q4. So, Q2 upon Q2 plus Q4 is x1. So, this is x1. So, x1 is a fraction of amount of total heat which is received to the cycle 1. So, obviously Q4 will, if x1 is the received heat corresponds to Q2, then 1 minus x1 is the fraction of heat which will be received, which is Q4. So, 1 minus x1 is Q4. Then eta is equal to eta 1 into x1 plus eta 2 minus eta 2 into x1. So, we will have eta is equal to eta 2 plus x1 into eta 1 minus eta 2. So, let us keep this equation in our mind and then again derive for the coefficient which is x2. The same expression eta we will try to derive with respect to coefficient x2, and then we will know that x1 is equal to 1 minus x2 and that is equal to Q2 upon Q2 plus Q4. Having said this, we can write down the expression as eta is equal to eta 1 into 1 minus x2. Now, x1 is equal to 1 minus x2 into eta 2 into x2, and this is 1 minus x1 is x2. So, this is done. So, knowing this, we can expand this and we can write down it as eta is equal to eta 1 minus eta 1 x2 plus eta 2 x2. This leads to this formula which is equivalent to this. Instead, only fact that we have now it in terms of x2 and this formula is in terms of x1. So, let us analyze these two formulas. By analyzing, we mean that let us feel that if eta 1 efficiency of cycle 1 is greater than efficiency of cycle 2, we can use this formula where eta 1 minus eta 2 terms come into picture. So, this leads to a number which is a positive number, but this is a fraction. So, this number will be less than 1, and since this number is less than 1, eta is going to happen to be not greater than eta 1. So, we will have eta 1 greater than eta 2. Similarly, let us feel that eta 1 is less than eta 2. So, we can use this formula which leads to this number as a positive number, but it will be less than 1, small number, and then this gives an impression which says that eta 1 is less than eta 2. So, it turns out with the fact that we should not consider two cycles in parallel, since the resultant cycle will have efficiency intermediate to the efficiency of two cycles. So, this was an exercise where we had thought to see what would happen if two cycles are in parallel to each other. So, understanding this, we will note the advantages of coupled cycle. We have seen that when two cycles are coupled, like topping and bottoming cycle, this is what binary or tertiary cycles, then we will have overall efficiency higher than any cycle. This is in particular for the gas turbine and steam turbine cycle. When we combine these two cycles, basically 2/3 output is from gas turbine, 1/3 output is from steam turbine, then there is reduction in investment cost by around 30%. This is a statistical input. Small amount of water is required for cooling the water, so water requirement gets reduced. we have great operating flexibility when we have two cycles coupled with each other. Then we can actually have installation in phases for the coupled cycle. Then we have also simplicity of operation of the coupled cycle, and we have lower environmental impact since our exhaust temperature would be lower in that case. We further have advantages of cogeneration of heat and electricity. We can use it like the case where we are having two cycles, one cycle is losing the heat, or we can have also usage like cogeneration where the water is source or steam is source of high temperature. So, such are the advantages of coupled cycles. Now, we are going to see what do we mean by low temperature cycle. Practically, we had seen that till time we work with the Brayton cycle or the Rankine cycle, where the temperatures at the combustion chamber or in the heat exchanger T max of the cycle is very high, and then that's where we had put the limit on the metallurgical case or metallurgical limit for the T max. But it's such T max was possibly obtained by combusting the conventional fuels, where we are having the coal or oil kind of fuels to be burnt. However, we might have some ready-made source of heat available from the industries waste heat, or maybe from radiation of sun. So, we can make use of such heats and we can run the Rankine cycle to obtain electricity from that. So, in such case where we have limited amount of the temperature difference available or limited amount of heat is available, then still we would like to execute the Rankine cycle. Such cases we are terming them as the low temperature cycles. So, let us see how the low temperature cycles would be operating. So, as what expected, we will have 1 to 2 in the case of turbine, then we have 2 to 3 in the condenser, and then 3 to 1 is in the pump, and then we will have 4 to 1 into the condenser boiler. So, this was the routine operation of our Rankine cycle. This was for electricity generation. But here you should see that in the boiler we have low temperature heat source which is heating our working medium. And obviously, when we are seeing that we are having this special topic of low temperature cycles, we will see that water will not be the first choice for these cycles. Then this is the source of heat for low temperature, and similarly we have cooling tower for the condenser, or we might have the low temperature sink also. Then Rankine cycle can be thought to be best used for the available energy resources. Then what are the possible available energy resources? We can have some industrial process which is having heat as lost to the atmosphere. We can have hot water from the geothermal reservoir. We can have solar radiation absorbed in solar pond, and then these will give us required small or sufficient temperature difference where we should be able to run a Rankine cycle. Rankine cycle in such cases will have low efficiency and in turn would lead to large components and high capital cost. This is the disadvantage, but we are trying to use the available energy as the waste energy or the available energy in the form of solar or geothermal for electricity generation. So, we are not burning any extra fuel. So, the most cost which is over here is in capital sense. So, we are saying that capital cost would only be higher and running cost will obviously be less since we are not in need of fuels. Having said this, refrigerants are the working fluids for low temperature cycles. We are going to demonstrate that why refrigerants would be good in low temperature cycles. So, we will see the comparison of steam and R314A, which is a refrigerant, when they are used for 1 megawatt turbine output and 90% efficiency of the turbine in case of simple Rankine cycle without any attachment. We mean here by attachment as superheater, reheater or regeneration. So, if no such attachment is available, then in that case we are considering that okay, we will have two working mediums and we have limited amount of temperature difference between the boiler and the condenser. So, let us see this. So, we have said that okay, we are having 90 degrees Celsius as the temperature in the saturation temperature in the boiler, we have 20 degrees Celsius temperature in the condenser, then we run our Rankine cycle. Then there are two working mediums, one is water and one is R134A. Then having said this, we have our usual conditions 1 to 2 here is in the turbine, 2 to 3 is in the condenser, 3 to 4 is in the pump and 4 to 1 is in the boiler. And here we mean that we are getting heat Q1 added, which is from waste heat or from solar point. Then these are the outcomes which we are going to get based on the properties of steam and properties of R134 corresponding to these two saturation temperatures. Looking at this, the first thing what we can see over here is the dryness fraction over here. We can see that the dryness fraction for steam is much lower than in case of R134A. So, R134A gives good dryness fraction at the outlet. This is good and this is not good. Further, we can see here that mass flow rate requirement of the refrigerant is high, but mass flow requirement of air of steam is less. But we should not just see the mass flow rate requirement. We can see the volume flow rate at the entry to the turbine and volume flow rate at the outlet of the turbine. Since specific volume of the refrigerant is very low, we can see over here that the volume flow rate at the entry to the turbine is very low for the R1 refrigerant. Similarly, volume flow rate at the exit of the turbine is low in case of refrigerant in comparison with the steam. So, it leads to that exit to inlet volume flow rate ratio is very less in case of the refrigerant. So, this gives us a very small requirement of a turbine. Turbine becomes compact since volume flow rate is small in comparison with steam. So, these two we can notice as advantages of use of refrigerant. Further, we can notice over here that we are saying that we are having 20 degrees Celsius as the temperature for condenser. For that saturation temperature, the R134 is having pressure 5.72 bar, but water will have pressure 0.234 bar. Similarly, steam will have high pressure, saturation pressure corresponding to 90 degrees Celsius as 0.7 bar, but in case of refrigerant we have pressure as 32.4 bar. So, these two pressures, one high pressure, one low pressure, or one boiler pressure, another condenser pressure, both the pressures are more than the atmospheric pressures in case of our refrigerant as the working medium. So, we have good dryness fraction, we have lower volume flow rate, we have higher pressures. So, these three things comprise to the advantages of use of refrigerant for low temperature cycle. But two disadvantages, what we can see that efficiency of refrigerant based Rankine cycle is lower than the efficiency of steam based Rankine cycle. Further, we can see that the boiler duty means heat added into the boiler and condenser duty means heat lost in the condenser, both are high in case of the refrigerant. That means we need more heat interactions in the condenser and the boiler if we want same 1 megawatt amount of work output using the refrigerant as the working medium. These two disadvantages are also there in the bracket of the refrigerant cycle. But here, as we should note again, that we are using the waste heat available from the industrial process. We are either using geothermal energy or we are trying to use the energy from solar radiation. So, energy which is said to be boiler duty is freely available for us, and we are not burning any fuel for that. So, noting this, low temperature cycles are used for electricity generations, although they supposed to have higher capital cost. There is one more option of low temperature cycle, and then that is called as ocean thermal energy conversion. Basically, we can think of having small temperature difference in the ocean between the surface of the ocean and its deep inside. So, if surface of the ocean and deep inside, if we try to consider, then there will be temperature difference. Temperature difference of 20 degree Kelvin or 20 Kelvin is available if we go 300 meter depth. Then in certain places we can get this difference where 26 to 28 degree Celsius will be our boiler temperature and 7 to 10 degree Celsius will be our temperature inside the condenser. So, this temperature difference can also be thought to be extracted for the work output or electricity generation, where such conversion of ocean energy is called as ocean thermal energy conversion. This is a possible power plant where we are passing our refrigerant in the circuit, where this is the refrigerant circuit. This is the refrigerant circuit for us, where we have pump. Refrigerant is getting pumped from low pressure to high pressure, then heat will be added into the refrigerant in the boiler, where basically boiler is comprised of the water which is taken from the surface of the sea, and that surface of the sea water is going to give heat to the working medium of our Rankine cycle. Then it will be passed into the turbine, it will rotate the turbine and it will rotate the generator, will generate the electricity, and then turbine's exhaust is given to the condenser. But in the condenser we are going to pass the water which is from the deep inside the sea, which we have said that around 300 meter. So, that water which is a coolant will rise its temperature maybe from 7 degree to 10 degree Celsius. The high temperature water will lose the temperature from 28 to 26 degree Celsius. Having said this, we can roughly plot our Rankine cycle over here, where we will have pump from 1 to 2, where we have pumping process from low pressure to high pressure. Then we have warm water from the surface of the sea giving its heat to the refrigerant, and refrigerant by all these means would go from this point to this point, which is saturation vapor line. Then we will have extraction of the work in the turbine, and then this refrigerant will lose it, but for that we will fetch the water from the deep bottom, and then this will be the cold water which will be gaining the heat. In this case, with the references where we will consider TTD, which is terminal temperature difference, to be the 2 Kelvin. If that is considered, then we can see that our cycle will have this kind of heat loss for the water from the sea surface, which will reduce its temperature from 28 to 26 degree Celsius, and it would gain the temperature from 7 Kelvin to 10 Kelvin, and then we would run the Rankine cycle of ours for electricity generation. Having said this, we can talk about the next point, where we are talking about nuclear power plant. So, this is a typical nuclear power plant where we are having our Rankine cycle as the basic cycle, but again we are considering nuclear power plant for the fact that we are having we are having the boiler where we are supposed to burn the fuel and having heat exchange is getting replaced. So, the point to be noted over here that we are trying to get the nuclear energy for the process of heating into the boiler. So, nuclear energy is our source of heat for the Rankine cycle. So, having this as our source of heat, we will see so maximum temperature. In such case, we will have basically based upon critical temperature of the secondary fluid. Here we are saying that there is water or steam which is getting passed in the circuit, which is basically boiler, pump, condenser and turbine. So, that circuit is called as primary circuit and working medium is primary fluid. So, in this case parallelly there is one more fluid which is basically passing the heat from the nuclear energy or nuclear rods to the water, which is our primary fluid, is called as secondary fluid. So, secondary fluid basically takes heat from the nuclear energy, a nuclear source, and then it gives the heat to the water. Here we mean that in case of ours, when we try to plot our Rankine cycle, in such case we will have it like this. We will have TS diagram, we will have the dome, and then we will have such as our Rankine cycle, which is very primary Rankine cycle, and that Rankine cycle will not be able to have superheat, which we have already discussed, since we are trying to say that we are having secondary medium as liquid, and if that is a working, that liquid is water, then water's critical temperature is known to us, then we cannot cross this temperature as the T max, since we are using water itself as the heat source. So, that water may be at high pressure, and then that high pressure water will supply the heat where we will go from 2 to 3 in the boiler. This is what we will go from 2 to 3 in the boiler. So, if we are trying to use liquid in case of nuclear power plant, then we have to be watching out with the critical condition of that liquid, beyond which we cannot have cycles T max. But what we can do, this the same amount of heat we can gain if we try to increase the mass flow rate of the same secondary fluid. We know that heat lost by the secondary fluid will be Q is equal to mCp delta T. So, we want same temperature difference between the secondary fluid and the primary fluid in heat transfer, then we can increase the mass flow rate. By increasing the mass flow rate, we can basically increase the amount of heat transfer to the secondary primary fluid, and by that means we can increase the T max, but still we cannot increase the T max beyond the critical condition. Having said this, we can think of gaseous fuels also as the fuels, gaseous fluids also for the heat transfer. But if we have liquid fluids, then we can know that for the simple Rankine cycle, turbine exhaust will be very wet. So, we will have very small dryness fraction at the outlet of the turbine. So, keeping this point in mind, we can think of other material than water liquid as the source. Then we can think of carbon dioxide as one of the materials for which is in gaseous format, can be thought as the medium for transfer of heat from the nuclear energy to the boiler, and similarly we can also think of liquid metals for transfer of heat from the nuclear source to the boiler. So, this would help to run the nuclear power plant where we are trying to avoid the use of conventional fuels like coal or oil to be used to generate the flue gases, which would pass over the water and generate the steam. So, instead of that, we are trying to run two circuits, primary and secondary circuit, where primary circuit is our steam cycle and that would receive the heat from secondary medium, which can either be gases like CO2 or water, liquid, or maybe liquid metals as well. So, this is the gist of nuclear power plant, how we can replace the conventional boiler. So, this ends the discussion on this topic, which is binary cycles and the nuclear or low temperature power plants. So, we will see the next topics in the next class. Thank you.